Alright, thanks for watching, and today I want to solve another very important PDE called the wave equation. And the wave equation, at least in one dimension, it's given by utt minus uxx equals to 0 with initial position g of x and initial velocity h of x. And here what's important is that those two functions here are given and our unknown is u of xt. So a function of two variables here. And this is super important because what does u of xt measure? It's the height of a wave at position x and at time t. So suppose you're fixing time t and you have some sort of a wave, which could be anything: sound wave, light wave, water wave, or other waves, or even, think of like vibrating solids or something. Then the height of the wave, it's given by u of xt. And as I said, we can explicitly solve this, and it actually has a very elegant formula in the end, which is called D'Alembert's formula, or as my friend likes to call it, Dilbert's formula. But not the same thing, okay? Alright, so how do you solve this? It turns out what saves us here is a very nice factorization based on the following fact, that t squared minus x squared, so if you replace tt by t squared and xx by x squared, you get that this is the same as t plus x times t minus x. Okay. And now we want to do the same thing, but with sort of differential operators. So on the one hand, utt minus uxx equals to 0, but in terms of doing the process of differentiation, you can write this as take the derivative of t twice minus take the derivative with respect to x twice. So suppose you have a function u and you apply this differentiation operator, then you get utt minus uxx, and that equals to 0. And as I said, you can actually write this in terms of a factorization. Namely, it turns out that this is true, that it's the same as d over dt plus d over dx times d over dt minus d over dx u. And let me clarify what this means. This thing means, first, take the derivative of u with respect to t and take the derivative of u with respect to x. In other words, that's the same thing as saying ut minus ux. If you take the function ut minus ux and differentiate this with respect to t and add of the derivative of this with respect to x, then indeed you get utt minus uxx, which is 0. I'm not going to do the calculation now, it's a simple verification. Why is that important? It suggests that we somehow use another function v, which is just ut minus ux. So, step 2. So let v be ut minus ux. Based on what I said, we find that v satisfies a new equation. This thing just says that vt plus vx equals to 0. Alright, and you might say pi m, okay, this is all in good, but all you did was just define new terms. How does that actually solve our problem? Well, interestingly, notice our new function solves a much simpler differential equation called the transport equation. And in fact, I have done a video on the transport PDE. Because the nice thing about this PDE is it has a very elegant explicit solution. So let me recall, or maybe you haven't seen this before. Okay. The solution of, in general, let's do it in one dimension. So Vt plus B Vx equals to 0 with initial condition, let's call it A of x, is V of xt is A of x minus tb. So in other words, it says that the solutions are constant on a line, directed by b comma 1. And again, I leave the details to another video I've made, but the nice thing is now we have an explicit solution of v, and let's just compare this and this. Well, it's the same thing, but with b equals to minus 1. So what we actually know is that v of xt is A of x minus t times minus 1, so x plus t. And I'm so sorry, so I was confusing this with something else. So here, b is 1. If you just compare this, and so v of xt is just A of x minus t. So x minus t times 1. Alright, this is good, except that we don't know what A is, but in the end we'll figure it out based on our data. Alright, wonderful. So we have our explicit formula for v, and the question is, how can we figure out u? Well, just using this equation. So now, let's go back to u. It was a very quick step too, but the magic of PDEs helped us. So step 3. Now use the fact that v is ut minus ux. So what we really get is that ut minus ux, based on our formula for v, that is just A of x minus t. You might say, okay, what about this? Can we solve for u? In fact, we can, because this is actually another transport PDE. In fact, if this were 0, you would just get the transport PDE as I talked before, but the only difference is we have this inhomogeneous term, but we're still able to solve this in the other video. So here's another fact. So the solution of ut plus, in this case again, one dimension, bux equals to f of xt, and u of x0 is g of x. So I should have put another function here, like c of x, but in fact, remember the initial condition is that. So it turns out we can solve this. That just gives u of xt, just as before, we had this g of x minus tb, and the only difference is now we have to add this running cost, which is f of x plus s minus t b comma s ds. Wonderful, and the interpretation is this is sort of the initial cost, and g is like constant on a certain line, and this is sort of the running cost, or like the price you have to pay from going from 0 to t. All right, and the question is, how do the two compare? Well, notice f is just a of x minus t, and b is minus 1. So b is minus 1, and f of xt is a of x minus t. So in other words, to get f is just a of the difference of the two variables. And now let's just do that. So our solution then becomes u of xt is g of x minus tb. b is minus 1, so you get x plus t, plus integral from 0 to t of f of just the difference of the two variables. So x minus s minus t, because b is minus 1, and minus s ds, and that's g of x plus t plus integral from 0 to t of, so f of t minus s, so f of x minus, I don't know why I wrote f, but it should be a. A here. So x minus 2s plus t, yes. And now this looks pretty ugly. Let's just do a simple change of variables. So let's just s prime be this whole junk. So if you want x plus t minus 2s, then ds prime is minus 2 ds. So ds is minus 1/2 ds prime. And s prime of 0, that's just x plus t. S prime of t, that's x plus t minus 2t, which is x minus t. And so we get something a bit neater. So g of x plus t minus 1/2 integral from x plus t to x minus t of a of s prime ds prime. And so u of xt is g of x plus t plus 1/2, and just reverse this, x minus t to x plus t of a of, let's just call it s again. This is wonderful. It's a much nicer formula, except again for the fact that we don't know what a is. But now, as I said, we will figure it out from the data. And remember, we had two things. U of x0 was g, and ut of x0 was h. Well, if you try it out and you calculate u of x0, you get g of x plus 1/2 integral from x to x, which is 0. So in the end, you do get u of x0 equals to g of x. This is great, but it doesn't solve your problem because you don't know what a is. But now, let's just use the other thing. So we want to use ut of x0 is h of x. Well, let's take this equation and differentiate this with respect to t. Remember, g is just a function on one variable, so this becomes g prime of x plus t. And for this, what we want to do, we want to use the fundamental theorem of calculus. So this becomes a of x plus t, and then minus, so a of x minus t. But because you differentiate that, you get a minus 1. And so we get g prime of x plus t plus somehow the average of the a's. So x plus t plus a of x minus t. All right. Now, let's just Still complicated, but remember, we want this at t equals to 0. So plug in t equals to 0. On the one hand, we get ut of x0, which is h of x. On the other hand, we get g prime of x plus 0, which is x, plus 1/2, something kind of cute, a of x plus 0 plus a of x minus 0, which is a of x plus a of x. So h of x equals to g prime of x plus 1/2 of 2a, which is a. And this is very neat. It allows us to solve our equation in terms of our data. So a of x, the stuff we wanted to find, is nothing else than h of x minus g prime of x. This is very good. We figured out our a, and now our last thing is just plug it into our original thing. I guess it's step 5 if you want. Now, okay. So step 5, again, what have we found so far? U of xt is g of x plus t plus 1/2 integral of x minus t, x plus t of a of s ds. And that now becomes g of x plus t plus 1/2 integral of x minus t, x plus t. Use this thing now here. So a of x equals to this. So a of s is h of s minus g prime of s ds. Okay, that's good. So it's g of x plus t plus 1/2 integral of x minus t, x plus t, h of s ds. And for g prime, you're taking the integral of g prime, so let's just FTC that stuff. So minus 1/2 of g of x plus t minus g of x minus t, which if you'd like, that's minus 1/2 of g of x plus t plus 1/2 of g of x minus t. But notice, this simplifies a bit. This cancels out halfway, if you want, with this 1 g of x plus t. So this minus this becomes 1/2 g of x plus t. And so what are we left with? And if you want, this is still 1/2 the integral of x minus t to x plus t, h of s ds. And so in the end, we are left with, indeed, D'Alembert's formula. So our conclusion is that, in fact, u of xt is 1/2 g of x plus t plus 1/2 g of x minus t. So let's just write it this way, in this elegant way. So the average of g of x minus t and g of x plus t plus the average, if you want, of x minus t, x plus t of h of s ds. Ta-da! So after this long derivation, but super elegant derivation, we have D'Alembert's formula. So not Dilbert, not D'Alembert, D'Alembert, which tells you that if you have a wave, the height of the wave is sort of given by the average of the initial conditions, but with time, plus 1/2 times also sort of the average of the initial velocity. And this tells us sort of how a wave propagates. And again, it was just based on this neat factorization and no integration by parts or anything. And But it does depend on this transport equation. So if you haven't already done so, I strongly encourage you to watch the other video on the transport equation. Alright, so if you like this PD adventure and want to see more math, please make sure to subscribe to my channel. Thank you very much.